So welcome to the second day, and today actually Claudia Tebaldi is with us, and she will start out giving her perspective on the science again and on probabilities and whether we can derive probabilities or not, I guess. Thank you.
So my idea for this talk is to tell you a little bit about uncertainty in projections of climate change and climate change impacts. And I want to do that by first talking a little bit in general about uncertainties as they are generated by climate models when we look at their output. And then I want to move on to talk about how these percolate down to our characterizations of impacts. And I want to do that, I'm thinking of doing that by talking about two concrete examples of studies that we have done recently. I have many people that I could have put down here as my collaborators. This is by no means my only work, and in particular for this work on crop yields and food security, I've been working with people at Stanford, David Lobel, Marshall Burke, Ross Naylor, Wally Falcon. And I'm a statistician by training, and all I know about this stuff is thanks to the people at NCAR that I've been working with for more than 10 years until recently, physically there, and I hope to continue working with them. So I don't know if I'm trying to spread the blame, but this is not only my work. There are many other people that are to thank for the good parts of this. So. What are the sources of uncertainty on the climate change side? And when I say climate change side, I'm thinking of the physical changes, the physical variables that characterize our climate. Of course, there are uncertainties that come from our inability to foresee the futures perfectly in terms of how much we are going to emit and at what rate. So there are uncertainties in terms of the boundary conditions to which we will subject the climate system. And of course, the first thing that comes to mind are uncertainty in our scenarios of greenhouse gas emissions going forward. There are uncertainties in what volcanoes will do in the future, because they may have some impacts, even if in the short term only. There are uncertainty about our changes in land use, in the solar cycles. So usually what people do with regard to these uncertainties is to condition their analysis of climate change projections to a specific scenario that hypothesizes precise paths in the future for these elements. There are uncertainties coming from initial conditions because we know that climate is not weather, but it is made of weather. So climate is an average over the behavior of weather over many years, over large spatial scales. But as weather is a chaotic system, depending on initial conditions, different initial conditions in our models produce slightly different trajectories. This is not really a big deal if we talk about 20 or 30-year averages sometime far in the future. So that's the way people address this uncertainty, by averaging model runs that come from initializing the models with initial conditions. But there is some intrinsic uncertainty that is much more difficult to get rid of, and it is the modeling uncertainty. And I'm sure everybody here is familiar with the concept of model and model uncertainty. I want to talk about what the specific uncertainties when we look at global climate models are. I'm not a climate modeler, as I already told you, so I give you, my kind of superficial description. Bill Collins here could tell you much more in-depth things about climate models. But when you think of these very complex, very sophisticated, very expensive climate models, you have to realize that even if they become more and more sophisticated and detailed, there is always some irreducible uncertainty, because by definition they always are going to have to make approximations. And the easiest thing to think about approximations here is that they have to discretize the system, the domain, both in time and space. And given computing limitations, the discretization is right now maybe on the order of 100 kilometers or 150 kilometers in the latitude-longitude direction, for example, and a few minutes in terms of the time step. Every process that lives and behaves at scales that are smaller than this has to be approximated. And this introduces irreducible uncertainties. And of course, modelers try to do their best and make this approximation as precise as possible. But different modeling centers produce different models because they have different solutions for this approximation problem. And it's hard to decide what is right and what is wrong, or maybe it's just that different solutions, at least for the current description of our system, work very well and then produce, unfortunately, sometimes significant difference when you actually look at the future behavior under those choices of approximation. I should actually say that I have a long talk, but I'm happy to stop at a certain time and let Steve do his job, and we see where we will get here. But or maybe you should tell me that I can go faster on this side and go to the applications. Feel free to jump in and tell me how to direct this. But anyway. So I told you how people address uncertainty in emission scenarios or initial conditions. When it comes to modeling uncertainties, there have been really two main approaches. One is to take a single model and to look at different choices for the parameters that describe those approximations. This is called perturbed physics ensemble approach. The other approach is to take different models, completely different models coming from different modeling centers and compare their results. I've worked mostly on the latter, and I think it's fair to say that these two approaches have been alternative approaches so far. And I think from the statistical point of view, the ideal world would be if every modeling center produced perturbed physics ensemble, so we could look at this, what somebody has called a super ensemble, which is many models, and within each model, many setting of parameters. So I think this, from what I understand, this workshop is concerned with decision making, and decision making usually happens at scales that are a little smaller than these 200 kilometers inside that is a grid box of a global model. So even if you start addressing those uncertainty at the level of the global climate models, you need to do something with this output that makes it more relevant for regional scales. And the two approaches that I know about is either to nest a regional model within a global model, and so you use a much finer resolution model of limited domain that is located over the region of interest. And regional models have been run, for example, for parts of the United States or for the entire North America. Or if you don't want to go that route, which is fairly expensive because these regional models, just because they are so high resolution, are very expensive computationally, people have tried to use statistics and relate the large scale to the small scale by fitting empirical relationship based on observations, so that those same relationships that are fit between the large scale and the small scale on observation, they can then be applied to model output and derive fine scale information from this model output. I'm citing here NARCAP. I think Steve is going to talk about it. It's an experiment that is going on right now where different different global models are forcing different regional models. So this is, again, an example of multimodal ensemble that tries to address uncertainties in the big models and the small models, because the small models as well have the kind of uncertainties we were talking about. There is also some interesting experiment that is starting right now, and actually the regional model is located over the western US. And it's regional models that are nested within the Hadley model center, the Hadley Center model, global model, with perturbed physics variations in its setting. So these are two variations on the idea of multimodal and perturbed physics at the regional level. I think it's fair to say that when it comes to now looking at impacts, doing work on impacts, there is more and more awareness of the problem of uncertainties in climate change projection. There are more resources that are devoted to computing and to run this kind of experiments. And so if until a few years ago, I think it was easy in the literature to see examples of impact analysis that were based, for example, on looking at the output of a couple of models that maybe spanned a certain range, and you were answering the question by looking at two very different answers in terms of the physical changes in store. Now there is more and more work on the impact side as well that tries to explore the uncertainty in a more systematic way. So what people do, maybe they have 20-something global models. They have 6 or 7 regional models. They may try to span the entire range of results that come from these very complex experiments. I'm a statistician, so I mainly work on trying to describe the data through a statistical model and provide formal probability distribution of climate change that then can be fed into impact models. My personal impression, and I wrote it down there in red, even if it doesn't show up in red, is that it's work in progress. For now, I think it belongs to the realm of methodological development. I'm not by any means claiming that what you'll see now in a couple of minutes are the true PDFs that describe our future in terms of climate change. Different statistical assumptions provide or result in different probabilistic description of our future. And I'm a Bayesian by upbringing, let's say. And it's one of those cases where your a priori decisions shape the result because the data, the observations are not constraining enough your results. And so these are the caveats that I want to put forward. So I don't know how much time I have. Can somebody tell me?
Yeah.
So
20 minutes?
20, oh, okay. So my idea was to give you a couple of examples of impact analysis. One that uses a formal statistical description of the uncertainty and was published in the Geophysical Research Letters last year. It's work with David Lobel and addresses changes in crop yields at the global scale. And another one that is based on a much simpler descriptive analysis where we just take the range of results from the global models that have provided their output for the IPCC. And we talk about food security by mid-century in different regions of the world. And you would wonder why does she think that those are enough detailed references for us to go and look for this stuff? No, I didn't mean to say that, but I wanted to point out that the second descriptive analysis that is a much simpler and much more straightforward handling of the results of these global models made it into science, while the first one we tried, we tried to submit it to, I think, PNAS and Science, but it was rejected because the reviewers thought that there was too much arbitrariness in our treatment of the data through this formal statistical model. And I think it's a good story because it tells you, I mean, in a way, I agree with that. I think these kind of journals that are announcement journals don't like to present stuff that is explicitly based on particular assumptions, and those assumptions are kind of difficult to interpret for non-expert in the field. But my claim is that actually, even when you take the range of results from the IPCC models, or their mean, or their quantized, you are making assumptions. You're just not making them explicit. Anyway, so the first example, the idea was to, first of all, describe climate projection probabilistically through a formal statistical model, build statistical models also of the relation between crop yield change and climate change, and then put everything together so that at the end of the day, we would have probabilistic description of the expected changes in crop yields under scenarios of climate change. And so, the first problem was to say something about what average temperature and precipitation would do by a certain time in the future under a certain scenario for a given season, and then to translate these into impacts on agricultural production. And our data was, of course, observed temperature and precipitation, climate model output of temperature and precipitation, and then data that collected over the last 50 years, crop yields for different crops all over the world, and at the same time, the climate variables associated with those crop yields. Now, I don't want to go through the actual statistical model. I just put down the slide to prove to you that it was actually a rigorous statistical models with all the assumptions that you have to do when you start thinking about the likelihood of your data, the priors for the uncertain parameters, the biases in the models, how do you characterize that, how do you characterize the variability of a given model around the true signal. And then I also, I think, put some equations, again, just to bring home the fact that this is a statistical model, and it's probably the reviewers in Science or PNAS thought that it was a little difficult to espouse these particular assumptions. We are just saying that we think the true climate signal is out there for both present and future. We have observations that tell us something pretty precise about what's going on right now. We have climate models that are approximating what goes on. The climate models may have some systematic bias, may have specific variability. We formalize all that, and at the end of the day, we come up with probability distribution function for future climate temperature and precipitation in terms of time series or in terms of just a snapshot of changes. I'm sorry, I'm going quick through this because I don't think it's really the point to explain to you this specific statistical model. My point here was to say we come up with formal PDFs that are not just empirical histograms of the individual model projections. It's a continuous PDF. It's a joint PDF of temperature and precipitation. You can look at it as a time series, as I said, or just snapshots of changes. Then you have, you can sample from this PDF, and for a given time in the future, you may have, many realization of possible changes in temperature and precipitation consistent with your assumptions on how climate model output relates to the real climate that you are out to estimate. And then you have a relationship between temperature or precipitation change on the x-axis and yield change. So here we have time series of yield. In this case, it's barley. It's aggregated globally. It's over 50 years, so there are 50 points on that scatter plot. And what we do is we take the year-to-year variation so that we get rid of the systematic trend that may be due to technological advances and all that kind of stuff. And we do the same for temperature and precipitation. So we are trying to estimate what yield does when temperature or precipitation change. We can do this, again, an assumption as a simple linear model. Change in yield is just a linear function of change in temperature and precipitation. We will estimate that. And then we will have the new temperature and precipitation changes coming from our probability distribution functions of climate change. We can plug those in that model, in that linear model, and come up with an estimate of yield change. I put up this pretty map because the FAO has these beautiful data sets where they tell you where people grow different crops and what's the percentage of area assigned to that crop. And you can look at what the climate is from your climate model or from observations in that area. Let me just switch to that. So, by our statistical analysis, we come up with a contour of changes in temperature and precipitation by 2030 or 2050. This is our representation of the future. We can sample different delta T's and delta P, temperature and precipitation. We can plug them in our estimated coefficient for the change in yield and come up with as many samples of changes in barley yield as we sample from our contour of climate change. And we can produce a PDF of change in crop yield. In this case, it's a negative change that goes from 0 to up to 20% losses in barley. And this is if we know exactly what the relation between temperature and precipitation and yield is. Of course, you can do the same kind of uncertainty analysis on that part of the problem, because by, for example, bootstrapping, or in this case, it's a linear regression, so you can actually compute exactly the uncertainty. You can find different values of the coefficients for slightly different realization of your data. So here I'm just showing that there is uncertainty in these coefficients. And so, you can put yourself in the other case and say, if I were exactly sure of what temperature and precipitation change is, I can just worry about the uncertainty in crop yield and how that relates to temperature and precipitation. I find a much narrower PDF, in this case, of yield change. And I can compare that with what I got from the uncertainty only in climate change. And then, of course, I can put everything together. And the result is interesting because it shows you that actually the dominant factor is your uncertainty in future projections of temperature and precipitation change, is not really the uncertainty in the relation between crop yield and temperature and precipitation. OK, so I don't want to talk about CO2 fertilization, except that there is not much uncertainty on that. And all it does is really shift your PDF. So in this case, CO2 fertilization by 2050 has the nice effect of obliterating your losses for barley. It's not the case for other crops. For example, for corn, which is the central row, CO2 fertilization doesn't work. So the different box plots are if I only look at uncertainty in climate projection, or only in as how the crop relates to climate. I put everything together in the red box plot, and then I apply CO2 fertilization. The box plot doesn't move, and maize or corn is projected to actually incur very significant losses under climate change. As I said, this made it in geophysical research letters. And now in the last few minutes, I just wanted to give you an idea of a much more straightforward analysis that we did for the sake of characterizing food security by mid-century. And of course, we started with the question, where are the biggest food security impacts of climate change are likely to occur? And so where should adaptation efforts focus? And of course, we went through sub-questions to address this, which of course have to look at where the hungry population is, what do they eat, and how do the crops that they eat will respond to climate variation, and how will climate change over these specific areas where these crops are grown. And so we went and identified different regions of the world based on the diet of the hungry in these regions, and we looked at the statistics of how many people are malnourished in these areas and what kind of percentage of the world population of malnourished they represent. And then we went and looked at their diet, and we collected the same kind of data I showed you before for this kind of crops. And the statistical model for the relation between yield and temperature and precipitation is exactly the same that you already saw. It's a simple linear relationship based on historical data. Now, instead of producing that complicated contour of temperature and precipitation change on the basis of that statistical model, we just take the IPCC projections for different models and we plug them in. This is something I showed you before. So we have 20 climate models. They give us projections for the regions where these crops are grown. We have a statistical model for the crop. We can do resampling over the uncertainties of the statistical model for the crop. We come up with projections of changes in all these crops that are characterized. You cannot read, and I'm sorry about that, but every box plot represents a particular crop in a particular region, and it gives you a representation of, vulnerabilities of different vulnerabilities of this crop. And the one that seems to have the larger loss is South Africa corn. So you go through all these fairly descriptive analysis, and you can rank different crops and different regions on the basis of their vulnerability. And then, of course, you have to decide what are your criteria for concern, right? And you may decide that you want to look at crops that have more than 95% chance of production losses, or more than 50% of production losses greater than a certain threshold, more than 5% chance of production losses greater than a larger threshold. And depending on your criteria, you can rank different regions and different crops. And this could be a way to rank your resource or allocate your resources to address this. All I wanted to say here was that this is a much more, as I said, simple and straightforward analysis. We just take at face value the output of these GCMs, and we don't ask if we are representing the entire range of uncertainty with those, or we don't even look at how they do for a current climate and try to rank them according to some criteria of performance or reliability. But this study made it into science, and so now everybody knows what's going to be food security in the future based on this analysis. Again, just the point that I'm the first to say that this work on try and characterize uncertainties from climate models through statistical, rigorous, formal approaches is work in progress. And I come up with my PDFs, and then Steve goes in with his assumption, and his PDFs are slightly different. And then somebody in England uses perturbed physics ensembles and comes up with a completely different representation. So it's true that different assumptions give you different results. But I just want to make the point, we don't have to forget that even simple mean and ranges have lots of assumptions within them. So as I said, I was not here yesterday, and I apologize for that. I hope this was minimally relevant to what you've been talking about, and I look forward to the discussion today, and thank you for listening.
Thank you very much, Claudia. And it definitely does fit in. So uncertainty, PDFs are better than nothing, right? And then we actually talked about the problem that very often we don't know the probabilities and how we might actually have a framework to deal with uncertainty about the probability distribution. So that is exactly something you also implicitly mentioned. There are different people deriving different probability distributions, and we looked actually at these kind of models that try to deal with it. So we have a second. Oh, you're already behind me. Yeah, please give your. Yeah, we all together.
Well, I also am a statistician. I work at the National Center for Atmospheric Research, where I'm working very closely with Linda Mearns and some other scientists there who are focusing primarily on regional climate, and that's what I'm hoping to talk about today. Thanks, Michael, and everybody for the invitation, and thanks for listening to what I hopefully have to say here.
You mentioned Carrie Kaufman, who's a faculty member in the statistics department here, and who couldn't be here because she has a conference in North Carolina today, but I just wanted to mention her work.
Yeah, I was actually supposed to be there at that conference as well, so anyway, I'm going to mention Carrie here in a minute because much of what I'm doing is work that we worked on while Carrie was a postdoc at NCAR, and as Michael has mentioned, now she's here at Berkeley. So I'll give you a quick view of NARCAP, what the goals are, what we're trying to do, what it actually is, and then I'm going to talk briefly about two analyses that we've done to kind of start looking at the output from the NARCAP experiment. So Michael pointed out yesterday, I think very nicely, that we come up with these measures of how global temperature is going to change over time, but in reality, that number is sometimes hard to think about if you're interested in water, or you're thinking about crops, or you're thinking about skiing. One of my favorite things to think about when I talk about this stuff, you want to kind of get a more local view, right? So a 2 degree global increase in temperature, as you pointed out, it could be 5 or even 10 if you're talking about the Central Valley. And GCMs are very good at kind of thinking about what's going on large scale impacts. But so here's the state of Colorado. If we look at a typical GCM, there's about, 4 or 5, maybe 6 grid boxes that cover Colorado. Now, Colorado is a pretty diverse place. Almost the entire eastern half of the state is basically plains, and then you get into the mountains. And these 2 red dots here, one of these is Denver, and the other one is Breckenridge. They're only separated by about 80 miles or so, but you couldn't think of pretty much 2 very different climates. Denver's on the Front Range, Breck's at 10,000 feet. Of course, my own bias of trying to understand whether I'm going to get to ski next summer or not. But one great big grid box is not going to basically be able to tell me the differences in what might happen in those 2 climates. So if you're thinking about impacts, heat waves, drought, floods, whatever, maybe the GCMs are giving us information, but maybe not enough information to make those statements on more local levels. So I am, Claudia hinted about downscaling. I'm going to talk primarily about downscaling, and basically using information from the GCMs to say something about what goes on at these local levels. Statistical downscaling, oddly enough, is not what I'm going to talk about today, but that's basically using some sort of empirical relationships to connect information coming out of the global climate models and to say something about what's going on local levels. Dynamic downscaling, on the other hand, actually uses high-resolution climate models. They incorporate all the same kind of physics and things like that, and they can show to reproduce a lot of different climates. There is a price to pay, for the computational burden of moving from a global climate model to a regional climate model. So some things do have to change. Not going to go into that in great detail because other people, as Claudia said, I'm a statistician. There's people in this room who know more about that than I do. But if you kind of think about say these regional models that I'm going to talk about on a 50-kilometer resolution, then you see Colorado now has quite a bit more information what might happen at local scales. And again, you kind of see Denver and Breck here kind of maybe isolated within their own grid boxes. So I'm a part of something called the North American Regional Climate Change Assessment Programs. I'm fascinated now by acronyms and everybody who actually comes up with the acronym first, simply because they can Google it and it shows up before anything else, and then they try to come up with the words to fit the acronym. I'm not sure Linda did this here, but you pretty much Google NARCAP and there's really only going to be one thing you find, the North American Regional Climate Change Assessment Program. It includes basically all the major climate modeling centers across the US, funded primarily by NSF, but some other money coming in from NOAA, DOE, and EPA. And basically, this is straight out of the proposal: systematically investigate the uncertainties in regional climate scale projections of future change. And the basic setup here is to take a number of different global climate models, use those to provide boundary conditions for the regional climate models. So as a statistician, I kind of start thinking, wow, you've got some known sources of uncertainty here, the different global climate models, the different regional climate models. So maybe what we should do is try to think about how those uncertainties in the different GCMs, how those uncertainties in the different RCMs kind of affect the final output, and can we cut up that uncertainty, if you will, in a way where we can attribute a certain fraction to the GCM, a certain fraction to the RCM, and try to understand what's really going on here. So this is kind of our table, our design matrix, if you will. The 4 global climate models are up here. There was also a run using reanalysis data just to kind of start things off, to kind of give us a sense of what's going on with potentially just a best case scenario, what goes on with the biases in the models, that sort of thing. And then 6 different regional climate models and 2 different time slices. Now, regional models are embedded inside of global models. So the boundary conditions come from the global models, and those are used to force the regional models. So every 6 hours, the regional models are kind of getting some information from the global climate models. Time slices, on the other hand, are simply just high-resolution global models, just simply the atmosphere-only component. Oceans are derived in another way. In fact, they kind of use current sea surface temperatures and then information about how those sea surface temperatures change from the global model. So I'm going to talk a little bit about time slices a little bit later on, but we'll focus on here. As you can see, this matrix is incomplete. Of course, we didn't have enough funding to actually do the entire matrix, which is okay. And what we actually came up with was a kind of a statistical design, a balanced half fraction. And so you'll notice that every GCM has 3 regional models paired up with it. Every regional model is used twice, so in some sense we're going to kind of get, good statistical properties, or our idea was having some good statistical properties to kind of parse these sources of uncertainty. The movie, well, my movie didn't work, but I have it over here. I think it's kind of interesting to kind of take a look at these things. This was one of the first things we did, just to try to visualize what was really going on here. Let's see. It came up a minute ago. Oh, it's already up. Apologize. So what we see here is an animation of January precipitation. And the frame here on the left is actually the INCEP data. So think about this as the global model. Okay? The NARCAP domain here is shown. And so basically it's pretty much all of North America from basically northern Mexico deep into Canada. And so what you see here is in the animation on the right is actually the ECPC regional model that's kind of been embedded inside of this global model. And the animation is kind of interesting. You can immediately kind of see that impact of what the higher resolution buys you. You can kind of just stop it just about anywhere. You kind of see, say, a storm system coming through the Pacific here. You see that same storm system and how the regional model gives you more detail, more resolution about what's actually happening in that storm system, at least in theory, right? It's supposed to be giving you more information about what's going on at local levels. So every 6 hours, it gets information from the domain. This model also actually uses something called nudging, and 2 of the 6 models use nudging in various forms, and that's using information from the global model, also on the interior of the domain. So in some sense, you might think the ECPC model should be, have more fidelity to the global model than maybe some of the others, but I don't know. Anyway, it's an interesting visualization of what we actually get from the regional models. Okay, so I'm going to talk about a couple of analyses we've done, as I said, to try to start piecing out or parsing out these sources of uncertainty. I'll start with the simple INCEP experiment. Again, the 6 regional models, INCEP provided the boundary conditions. We're going to just simply take a look at 20 years of output and focus on average daily precipitation over the winter season, just December, January, and February. And basically, this comprises our data. Okay, so we have 20 different years, 6 different models, And in this case, all we were simply asking the question of, are the models basically giving us comparable information? Are they telling us the same story? They should be. They're all forced by exactly the same boundary conditions. They're basically all going after the same climate. Obviously, there's differences between the individual models, but they should be telling us the same story. So you might imagine that the columns, right, should basically kind of feel like realizations from the same distribution. Now, you know, if you think about this setup, right, if we were teaching Stat 101 right now, this would be exactly the way you might think about a simple analysis of variance, a one-way layout analysis of variance. And in fact, we could kind of proceed along those lines, okay? We could go into every grid box. We could say, well, here's my data in that a grid box. This one is in eastern Nebraska, and I can break that apart into a mean, these model-specific effects, and then everything that's left over, that year-to-year variation, everything that's left over. And if we want to ask the question, are the models different from each other, we look at these model-specific effects, and we simply ask that question, is the variation we see here, you know, larger than just kind of that year-to-year variation? So is the model-to-model variation bigger than the year-to-year variation? And we could plug this in, or have some graduate student plug it into our favorite statistical analysis package, whatever you want, and at the end of the day you'll get a analysis of variance table, spit out a p-value here, maybe put some stars here because this is a very, very small number, and you might conclude, yeah, sure, okay, at least for this grid box, these models don't look the same. There's some differences between the models. Don't really know what those differences are, just that there's some differences. And we might go ahead and crank through this thing and do that for every grid box. And if I just plot the p-values here, you see that basically over the entire domain it's bright red, maybe suggesting that these models are different everywhere. Okay, well, you know, if that's what you would have done, I wouldn't have given you more than maybe a C and if you were taking class from me, because there's an obvious problem here, right? And the problem is that these things are spatially correlated, right? These are not independent, the grid boxes are not independent of each other. There's very strong spatial dependence. In fact, what I went in is just quickly grabbed just the residuals, okay? So I just randomly picked a grid box, randomly picked one of its 4 neighbors, and simply plotted those ordered pairs for each of the individuals, each of the 6 models. And you see that that spatial correlation is very, very strong, okay? So, you know, basically any conclusions that you would try to draw from that point-wise p-value map would be faulty, right? Basically the situation is we don't have as much data as we might think we have, and so it's hard to say what might actually come out. If we were to do this in a more rigorous way, and this is actually the work that stems from the work that it does stem from the work from Claudia. Claudia was our original motivation, but this is the work that Carrie did or started to do while she was with us at NCAR. And that's, you know, we're going to do the same kind of decomposition, but we're going to think about these effects not as individuals, but as surfaces. And so we're still going to partition each one of those fields in that grid into something common, into something model specific, and then everything that's left over. And the innovation here is that we're going to consider the surfaces, okay? And so we've just bounced into the world of spatial statistics. We're going to consider each one of these effects as some realization from some spatial process, use some sort of Gaussian fields to set these things up. And if you go through all of that mess, you get a very different picture. I think my pointer just died. Do you have another one? And so what you see here is, as I said, a very different picture, and maybe this one starts to make a little more sense. You know, you kind of get some features here that might be related to the mountains, maybe along the coast. A lot of stuff going on up here, which I don't really have a clue why. We're still talking to some of the modelers to try to understand more about what we see, but now we start to see those differences, if you will, and we might have a little more confidence in that this map is maybe a little more representative, because unlike this map, we've actually tried to take that spatial dependence into account. And so we ultimately are generating PDFs, very much like what Claudia has done. It's just a little more difficult to conceptualize because now we have PDFs of surfaces. And so it's hard to kind of convey that information back on a map. So we're still kind of wrestling with those issues a little bit. But ultimately, we build one of these Bayesian hierarchical models. It turns out I'm not a Bayesian by training. In fact, quite the opposite. I'm a Bayesian of convenience, not a Bayesian of by training. Yeah, yeah. I even went back to my alma mater and gave a talk on this not too long ago, and I kind of made that crack that I'd gone over to the dark side because they were definitely not Bayesians. But in any event, the Bayesian paradigm actually gives us a way of kind of breaking things up into pieces and kind of thinking about all those sources of uncertainty in I think a reasonable way. So just, I don't want to bore you with the model itself, but we might kind of think about the way this model is constructed. We kind of argue that each one of those surfaces that I showed you in that initial grid, has some common mean to it. So there is kind of a model-specific mean, but we allow those to vary smoothly away from those means. So in the first level of hierarchy, we're just kind of taking into account that year-to-year variation. Then we allow each one of the regional models to kind of also vary around a common mean. Maybe a faulty assumption, maybe not, right? But basically we're allowing them to deviate from that common mean in a very simple way. Of course, a priori, we are saying they are all forced by the same boundary conditions. They are all going after the same climate. So is it dubious? Maybe not, but we are allowing for them to vary away from that mean. And then ultimately, we put a prior on that common mean that is related to the driving model. So we're trying to bring that information into play as well, but we're kind of saying, yeah, well, there might be things in common with the driving model, but we're again allowing the models to kind of vary off of the driving model as well. So now we're trying to get at that value added idea. So another way of thinking about it is, I might break each one of these guys down into the incept field, the driving model, okay, plus something that's common across all those models. So you might think that this eta term represents that value added in the ensemble. What is the ensemble giving me that I didn't already get from incept? So basically, what am I buying for my $5 million, right, to run this experiment? Then I add in the model-to-model deviations, and these, might be akin to some sort of model biases, right? We're kind of thinking about how the models maybe vary away from what's going on, and then of course, everything that's left over. Now with that in mind, we can do some comparisons. I'll just briefly go through those. So for example, this is where we're starting to get at that value added. What is that common component simply minus incept? And you kind of start to see, well, there's maybe more precipitation here in the mountains, some regions here, maybe it's a little bit less, the Sierras maybe a little bit more, although the nature of that precipitation is also a concern. Maybe a little more across the plains, a little less over here. Of course, we could have done that without this big statistical machinery, right? We could have just averaged these things together and taken advantage of it. But because we have these PDFs in our back pocket, right, this formal, rigid, rigorous, I don't want to say rigid, rigorous statistical analysis behind it, I have distributions that can describe this difference. So we can maybe say, okay, well, where is there a high probability that what I'm getting out of the regional model ensemble is greater than what I get from incept? And maybe you start to get kind of pictures like this, where we have regions where we are seeing significantly higher precipitation than what we might get out of incept, and that's kind of talking about things that might be going on in the mountains among some other areas as well. Let's see, what else do we want to talk about here on this one? We can also go after, I first started doing this, I kind of stopped at this one, right? Kind of stopped here and said, yeah, there's differences. And I kind of got yelled at a couple of meetings. Everybody wanted to know, well, which one is bad? Which one is worse? Everybody wanted to know, which was the model we didn't want to use. I didn't really want to go there, but we can take this to the next level and say, just like we would teach our Stat 101 students, you do the analysis of variance, you find a significance. Well, there's a next step that's saying we know that there's differences in the factor levels, but now we want to try to ascertain what are those differences. Okay, and so maybe we'll go into something that looks like this, and my graphics aren't really showing up well here, but let's just focus on this diagonal here. This is basically just simply looking at the probabilities where those model biases or those model-specific effects are greater than 0. So how do these kind of differ, if you will, from that common component amongst the ensemble? And just real briefly, you can drill in here and actually look in specific regions, but you can get kind of a top-level picture here. For example, if you look at ECPC, this figure is basically almost all red, although I'm not the greatest with colors either. I don't know what color that is, but it's basically almost all red, kind of suggesting ECPC is giving me more precipitation than any of the other models. WRF, on the other hand, is almost all blue. It's kind of at the bottom. And the RCM3, MM5 kind of are in the middle, and HRM3 and CRCM are also kind of in the middle. So we can now go in and not just say, well, there are regions where the models are the same or giving me similar information. There's regions where there's different information. We can drill down and actually understand where we are seeing model similarities and model differences, and again, in a rigorous statistical way. Now, the second experiment the second study I want to talk about is looking at heat stress, and now more of the NARCAP ensemble is coming online. We're starting to get the GCM, RCM combinations here, so we're actually starting to take this to the next level and think about projections of what's happening into the future based on this ensemble. This was a real early study that I did. I did kind of 3 different things here. I looked at temperature, precipitation, and then heat stress, right? So starting to kind of think about connections between climate and climate change and public health, right? So starting to think about what is the impact of heat is on morbidity, on mortality, heat-related kind of diseases, that sort of thing. Now here I'm simply going to compare 2 different types of dynamic downscaling. So you've got the GFDL-driven time slice. So again, this is a high-resolution global climate model, but it's just the atmosphere-only component. Observed sea surface temperatures are used, and then to get the future runs, they look at the deltas, if you will, the changes in sea surface temperatures as predicted by the global models, tack those onto the sea surface temperatures, and then run the atmosphere component into the future. And then the GFDL-driven RCM. So these 2 are kind of interesting because they inherit the same basic physics from the global model in some sense, right? So a priori already, you might expect these 2 to kind of behave somewhat like each other since their parent, if you will, is the GFDL global model. Both of these use the A2 scenario, and we're going to talk about current versus future. There's 30 years up to 2000, and then 30 years from 2040 to 2070. And we're going to talk about May through September heat stress. I'll talk about in a minute. What is heat stress? You know, I don't have a clue, right? It's kind of one of those things that I don't really know how to define it, but I'd know it if I see it, right? It's kind of one of, everybody knows when it's hot, everybody knows when it's really hot, but how you actually quantify that in a way that's meaningful is actually not well defined, I guess. So we fell back onto something that Claudia had done a while back with some global models, and that's look at the maximum of the 3-day running mean of overnight minimum temperature. It's kind of a complicated construct, right? But if it gets at persistence, right? Because it's kind of a three-day or more kind of feature. So it's not just one really hot day. It's a number of hot days in succession. And because we're kind of focusing on the low temperature, the overnight temperature, we're not only getting at persistence, but we're also getting at that the lack of the ability of the body to cool off at night, right? So if you are kind of in the lower socioeconomic classes where maybe you don't have air conditioning and you don't have kind of those resources that maybe other people do, this kind of measure might capture the kind of vulnerability that you might be kind of concerned about. Okay, so just to kind of give you a picture of what's happening here, this is just from the time slice, just 1980, 90, 2000, 2050, 60, 70, and you kind of see this big ugly red blob here in the middle of the country. And you see, if you look in these 3 frames from the future, that big ugly red blob is getting bigger and uglier and redder, right? As these things are moving up, right? The regional climate model, you see kind of maybe the same feature here, maybe not quite as severe, and it's not located in the same place, right? We'll come back to that in a minute. But the same kind of idea that it's kind of getting more pronounced and a little broader as we move into the future. And if we just kind of do some exploratory statistics, we can just look at the current, the future, the time slices on top, the RCMs on the bottom, and we just look at the difference. We kind of see from the regional model a change here kind of focused over Missouri, Illinois, those kind of regions, maybe something out here in the west. It's a slightly different location here for the GFDL model. I'll come back and explain more about that in a minute. So we're going to kind of take this functional ANOVA idea just a little bit further now, okay? Because now we've kind of gone to, the second half of the semester for our Stat 101 students. We're not talking about single factor ANOVA, we're talking about two-factor analysis of variance, right? Because we have two different models, we have current and future, and so we have a 2x2 setup here. The way we kind of think about this is we kind of have a baseline, we have an adjustment that actually explains the differences between the two models in the current, an adjustment that is the difference between the current and the future, and then an interaction term. And I'll come back and talk about those interactions in a minute. And again, we put priors on these things that allow for these kind of smooth deviations, the spatial dependence, all that good stuff. But we also build in information from the global models in our prior distributions. Again, this kind of idea that both of these have the same parent in the GFDL global model, so we use that GFDL model to give us some sort of prior information. We also did some work in the error term. This kind of handles the difference between current and future, but there's also business that goes on within the 30-year periods within each one. So we allow for some trends that come in, say, within those periods as well. So just quickly talk about some results here. So what we end up seeing is, say, within the current run, we see kind of over that 30-year period an increase on the order of about a degree. If we look in the future run, we see an increase just within those 30 years, something maybe closer to 2 degrees. Okay, so the rate of increase is also is kind of changing, if you will, within the 30 years of the current and the 30 years in the future. If we break apart these pieces, now these are just posterior means, we kind of see that main effect. This is that adjustment that explains the difference in the two models, an adjustment that kind of is the current versus the future, which is one we'll focus on, and then that interaction piece. One thing we quickly find out is the differences between the two models kind of dominates everything. So again, we kind of go back to the idea of where are the sources of uncertainty coming from here. We've got one source of uncertainty that's the difference between the two models, one source of uncertainty that's kind of the change from current to the future, and really what we see is the difference in the two models is actually dominating dominating the uncertainty or the variability in the output. Again, I'm going to come back to that in a minute. However, if we kind of put these on their native scales, even though there's some differences here, we see, this is just posterior means, but we do have evidence that interaction term is significant. Now, this is something we're still wrestling with, and I think it's kind of a profound statement because not everybody, but there's this whole industry on weighting models, right? How do we weight models in certain ways? And I think this kind of is problematic in a number of ways. Weighting models, if you will, is simply just a way of ranking models from the best to the worst, right? You're going to put more weight on the model that you like the best, and I'm not saying whatever your criterion is, it's a weighting. What the interaction is saying is that the biases perhaps in the models are changing from the current to the future, so that ordering is changing from the current to the future. So any weights that are simply based on some criterion based on current model runs are probably not going to work in the future, or it's not going to be surprising when they don't really tell you much about what happens in the future. So it really kind of, in my mind at least, is starting to say we really need to think about how we might weight models from the current to the future a little more carefully than just kind of some sort of something that solely is based on how current models kind of compare to data or something like that. It kind of throws some problems with that. Also, because of the interaction, it means that we have to be a little more careful about how we compare the models in the future. Oddly enough, when we just look at average temperatures, that interaction is almost nil. It doesn't seem to exist. There's maybe some evidence of some interactions around the lakes, the Great Lakes, but not much beyond that. Again, it oftentimes simply depends on what field you're looking at. If you're looking at average temperatures, maybe we don't see a lot of interactions. If you look at precipitation or these extremes, you see interactions. All right, so let's just kind of talk about this, how I might present this information to somebody who's interested in public health, who's interested in heat stress and how heat stress might change. This is just a single draw from the posterior of alpha 2. That's basically the change, right, from current to future. And I've basically just drawn that realization here, and I've drawn a contour line that represents an increase in heat stress by 3 degrees. 3 is somewhat arbitrary. And you know, you kind of get a sense of, well, that's pretty much all of the U.S., most of southern Canada. But of course, this is just a single draw. If I pull off, say, 20 draws and I plot the spaghetti plot, I start to get some sense of the uncertainty that exists in this particular contour. And so one of the things we wrestle with is just simply how to convey this kind of information. This is by no means the final guess here, but basically I've tried to put a bound on maybe where this contour might exist. So what you see here is the probability of an increase of greater than 3 degrees. The big contour is where basically every draw from that posterior that I made contained a 3 degree or greater increase. And the line, the thinner line out here is where there was at least one draw that contained an increase by 3 degrees. So we're kind of getting maybe at least some sort of probabilistic bound on where that contour actually may exist. Of course, it depends on what threshold you use. Here now I have the time slice. Here I have the RCM, varying that threshold from 2, 3, and then 4 degrees. And again, we kind of see that idea of that the interaction is playing the same. There is information that's coming out that's common between these two models, but there's also some differences between those two models as well, which kind of makes, as I said, comparisons a bit problematic. So to kind of wrap this up, what we looked at was just simply, can I highlight regions where these two models agree? Okay, and so what you basically see here in the red is where basically these two models agree on a change greater than 3 degrees. This kind of whatever this color is, this ugly color here, is basically where, you know, at least one of the models suggested a high probability of having 3 degrees, and again the same kind of contours. Now, I don't want to make a big deal out of this. What?
Why does it get warmer as you go north?
These are just the change from the current, right? But this is also a measure of heat stress. So this is summer. It's May through September measure of kind of extreme heat.
Okay, so just a heat stress measure, which is different than the increase in
And yeah, this is not just an increase in temperature. Yeah, so it's going after the extremes. Now it actually turns out, as we found out later on, is the GFDL time slice has got some problems. Right? It turns out, as a number of people have looked at this, I kind of said, you know, this doesn't really make any sense. This is saying very different things. The sense is now the soil moisture and the GFDL model is messed up. I don't know what that means, but basically they're kind of saying that the GFDL time slice is maybe a little less reliable than the other models, and in fact they're redoing it all. So I haven't tried to publish this, thank goodness, because it'll all change down the road a little bit. So again, the point is we're still trying to build methodology for regional models that kind of builds on the PDFs that Claudia has introduced, but kind of thinking of them more spatially so that we can go after the effects that Michael was talking about yesterday. So I will wrap up there.
So my talk is totally different from the previous ones, actually from all the others yesterday. I'm going to present a talk about the psychology of judgment decision making with imprecise information, vague, ambiguous, whatever you want to call it. I think it's the third time I find myself at one of these meetings where I'm the only psychologist in the audience, and I kind of have asked myself, why was I invited? And the obvious question is to provide some entertainment, which I don't mind, but I think I'd like to basically leave you at the end with a message that there is a lot to be learned from these kind of studies, experimental studies, small scale that we are conducting, and that has a lot to say about issues of how the results of the various models are being projected and are being interpreted and are being used by politicians, policymakers, and how they're understood by the public at large. So what I plan to do is to give you a little bit of kind of introductory background to try to say where I think this fits, and then I'm going to divide my time equally between two areas, some experiments where we ask people to make decision making with imprecise numerical information in the form of ranges, and about experiments or studies that deal with judgments with where probability is described by verbal terms such as likely, highly unlikely, and so on. So just to, again, for those of you who have never seen a JDM psychologist, what our work is really, it's experimental work primarily, and it focuses on the way individuals or small group, juries, committees, and so on, are making decisions. And although we are quite often borrow information from normative models, axiomatic models like the one we heard yesterday, the way to think about the distinction between what we are doing and what they are doing is that where they are trying to model the decision problem, we are trying to model the decision maker and to understand actually how he or she behaves when put in a situation that's being modeled by a particular axiomatic or normative model. So first of all, where I find this, where I put this work. You know, when I first took my first class in decision theory, I read Luce and Rafe, and Luce and Rafe, I talk about the three classes of decision situation: individual decision making, certainty, risk, uncertainty, or ignorance. And over the years, I came to realize that these are not really three discrete points. These are really, there's a continuum, and these points are of special interest, especially because they are easy to model and axiomatize. But in fact, you have to think of decisions as being along a continuum in terms of information. And what's of particular interest to us, to me, is that particular gray area that goes between risk and ignorance. And everything that I think that people are interested here is in this area. And the many situations that fit in there are cases where you have a second-order probability distribution rather than a precise one, where you have what people refer to here as multiple priors, which one model that generates multiple priors is the situation where you have several events. You can rank order them from the most to the least probable, but that's not enough to generate a probability distribution. There are many priors that could fit that order, so there's just one situation. Cases where you know probabilities, but you immediately qualify by telling them, but we are very uncertain about them. You can think of them more as guesstimates. Situation where you can bound probabilities from above and below, as such as you could say, if you think of the Koopman's model, or situations where essentially you are classifying cases into some fuzzy regions, such as in the 80s, greater than 60s, or likely, and so on. I want to say a word about terminology. That's a pet peeve of mine. So I looked up the terms ambiguity and vagueness in the dictionary, and you see that ambiguity is really refers to situations to a description that can be interpreted in more than one way. And I just want to point out there's nothing in Ellsberg example that fit. I mean, Ellsberg used the wrong term. What Ellsberg was modeling is not ambiguity, he was modeling vagueness, because there's nothing ambiguous about the decision of the urns in Ellsberg. But unfortunately, we are stuck with this. But I'm going to try to systematically use the word vagueness instead of what most people use, ambiguity. When I'm thinking of probabilities, I find it very useful to think in the terms of taxonomy of three sources of what are the sources of imprecision in judgment and communication. And I think it's important to distinguish. The first one is the nature of the event itself. I mean, quite often the problem in communication have to do not with imprecision in judgment, but in the ambiguity of the events that are being judged. And quite often people tend to assign probability to events that are poorly defined or ambiguously defined. The second level is, of course, the type of uncertainty, whether it is aleatory or epistemic, where it represents external sources that can be in principle quantified, or whether it represents internal incomplete, sense of incomplete or imperfect information. And the third component is the language by which the probabilities are being communicated. It can vary from very, very precise probabilities to very imprecise. And an important point to realize is that these three are not independent. In fact, essentially, I'm going to state the principle that decision makers are always best served if the uncertainty information is communicated to them in a way that matches the nature of the events and the underlying uncertainty. So as an example, consider how ridiculous a statement that the chances of an abrupt drop in the market in the near future is 0.2348. Now, the event is ill-defined because different people will understand abrupt and different people understand near future in different ways. Therefore, the idea of assigning to an ambiguous event where the underlying uncertainty is epistemic, a precise statement of probability shows you that you need to have a match, a congruence between the nature of the events and the nature of the communications. There are nice experiments, for example, this experiment by Ido Erev, where we show that people learn to adjust and choose the right way of communicating probabilities to match their goals. So an experiment where some people are seeing events, they are judging probabilities, they are communicating to another group of people who need to make decisions. The payoff for the decision is such that sometimes you get more when you reach unanimity, sometimes you get more when you have diversity. And over the course of the experiment, people slowly but surely, the probability communicators learn that it is to everyone's advantage to avoid precise communication and to use imprecise range because that fits the payoff function. There's also work that Mike Olson and I have done, which show that people, when they can choose to use various modes of communication of probability, they typically learn quite quickly to use probability communication that match the nature of the event on the underlying uncertainty. This doesn't belong here. So, okay, so let me talk a little bit about some experiments we did with vague probabilities. So this, everyone knows this is the Ellsberg two problems. And as a rule, you see the generalization that people prefer the precise one, or people avoid ambiguity, or in my terminology, avoid vagueness, and which is true. But I want to point out, by showing you the results next, that this is far from being a universal result. And in fact, this is not even such a strong result as many people expect. So these two plots summarize results from two experiments that Karen Kramer and I did, in which people essentially played the Ellsberg two-urn. So let's look only to the left. If you look at the left, we classify the decisions into decisions where follow the classical paradox, namely people choose the precise one twice. Things where people are consistent in the sense that they choose the precise urn in one case and the imprecise in the other one. Cases which have at least one of them they expressed in difference, so they're hard to classify. And this is the cases where actually people choose in the inverse pattern. In other words, they prefer the imprecise, the ambiguous urn on both. And the point to see is that yes, this is the vagueness avoidance is the mode, but it's never more than 35 or 40%. There's a sizable majority of people who are either consistent or express indifference, which means they're vagueness neutral. And there is also a sizable minority who actually behave in the opposite way. And this is just an extension where instead of having one urn being precisely known, 50-50, and the others being unknown, we are comparing urns that have both uncertainty or vagueness, but to different degrees, and you get the same result. And the other thing to notice is that the ambiguity avoidance is stronger when the urn is 50-50. If the known urn is 80-20 or 20-80, you have much, much higher levels of consistency with SEU, with subjective expected utility. So I'm going to skip this. As I mentioned yesterday in one of my questions, I became interested in the issue that there is so much preoccupation with the imprecision of the probabilities, but much less with the outcomes. And in fact, if you think about it, in many cases in real life, there is imprecision on both. And so, for example, the Casey and Schultz is a paper that talks about decisions about compliance with, in taxation context. So you ask yourself, can I claim a particular deduction? Well, there's a certain probability you'll be audited. There's a certain probability you'll be of course, caught and penalized. And you don't know the exact probability. It's an ambiguous probability, but you also don't know the amount of the fine or penalty you're going to face. So, and in other cases, Howard Kunrater did work with Jackie Mazzaros and others on underwriters who need to set up to underwrite insurance policy or things such as a new technological development or a new vaccine, where you don't know exactly what are the chances of a side effect, nor do you know exactly what's going to be what's the range of consequences, right, that such side effects might have. So what we did, we started, and there are a bunch of experiments that show that, in fact, people react quite similarly to those, and in fact, that the effects are somewhat additive. And we were interested in the issue of whether one source of vagueness is more important than the other. So if you had $1 million to invest in a problem, would you invest $1 million in order to reduce the range of probability or to reduce the range of unknown consequences? And so in some studies, for example, Paul Schumacher did some studies where he found that he asked people which one they would like to resolve when they had to choose between pairs. Most people prefer to reduce the probability. We did studies where instead of having paired comparisons, we asked people to come up with certainty equivalents to gambles. And in those cases, people are actually much more concerned with the outcome. So there's a beginning of a hint that things are not uniform again. So the first thing you need to do such a study, you need to have a scale, a metric of vagueness. In other words, how would you call two things equally vague or equally imprecise when they are on two different dimensions? And our definition, which you may argue is that we say that if you can induce vagueness in outcomes and probabilities, we're going to call two gambles equally vague if they span the same range of expected values. So for example, this is a gamble. You have a probability of 0.05, and the outcome is between $45 and $155. And the range of expected utility is 225 to 525. And that's a precise probability but vague outcome. And this is a gamble where you know that the probability is between 3 to 7% of winning exactly $75. And this spans exactly the same expected value. And the mid-range is 375, which happens to be the expected value of this. So we think of when we compare gambles, we think of these two as being equally vague. And we compare, for example, certainty equivalent of triples of this type. So here are the results from a study that's Du and Budescu Management Science 2005, where this was done in a context of presenting people with investment. So these are hypothetical securities, and people are told there's a certain probability that will go up by that much, and we manipulated the precision of the probability and the probability of and the outcome and the precision of the outcome. And what you have here these are median certainty equivalents for gains and for losses. So the first result that immediately strikes you that whatever effect you have in terms of ambiguity, they are much, much more pronounced for gains than for losses. Although I must admit that the monetary amounts here go from 20 to minus 20. So I'm not sure that holds for millions. But so clearly, whatever effects you have, they are more pronounced for gains than for losses. And the black bars, there are always cases where there is vague outcome. And what you see is for gains, people are always willing to pay more for the vague outcome. So actually, people like vague outcome in the domain of gains. There's a reversal in the losses. In the losses, people dislike imprecise outcomes. And what you find is that, again, in most of these cases, actually, the precision or imprecision of the probabilities is the least important. Okay, so to summarize these results, this kind of a general summary of that study, we find vagueness seeking for outcomes, for positive outcomes. There's a little bit of vagueness avoidance in losses. There's no strong attitude to vague probabilities, and if you compare the two, you can actually find that people are more concerned with outcomes. If you're looking at paired comparison, ask people to compare pairs rather than value them and come up with certainty equivalents, you get a slightly different result. And we have actually a model to do that. To explain this, we have a model which is an extension of prospect theory in which we introduce additional parameters to model vagueness. But I don't have time to go into that. So my generalization here is that what people think as effect of vagueness, saying, oh, vagueness avoidance or ambiguity avoidance, stamp it and push and move on, it's a mistake. I mean, I say, yeah, it's there, it's quite prevalent, but it's not quite as prevalent, and certainly not as universal as people think, nor is it of the same type in various cases. It's malleable, it varies if you ask people for gains and losses, it's different if you focus on probabilities and outcomes, and so on. Another study that I'm going to show you, it's a study where et al. Includes Rob and Klaus in this case, where instead of kind of focusing precise versus imprecise, we actually created a situation where we manipulated vagueness and we asked people to make choices between several actions. And the question was how they will make choices among these actions in the presence of imprecision. And as a side, there's also another component there of the way in which information is described. And this has something to do with climate change, because the various actions that people have to choose among were modeled to mimic roughly certain options that people have in climate change. So here's how we manipulate or induce vagueness. People come to the laboratory and they are presented with a bunch of urns of this type, in which there are already some balls. Some are red and some are white. And we tell them we've already put 30 balls in there. But in addition to these opaque urns, there are very large jars, transparent with white and red, and we tell them, please count 30 red and put them in. Please count 40 white and put them in. And now you know that in this jar there are 100, because we already told them there are 30 that we put there ahead of time, and you've counted 30 red and 40 white, so you know what's the lowest number of white and what's the lowest number of red, but you don't know in full the composition. And so that's what we call a vague situation, because you can put bounds on the probability, and then you have to need to make choices between them. And the choices, I'm going to present them this way, are essentially a risky, a riskless, and a reduced risk. People are endowed with a certain amount, E, and then if we draw 2 balls, which with probability P, they lose everything, so that's the risky. They can avoid this altogether by agreeing to pay a fine, and there's not going to be any draw, there's no danger whatsoever. Or you can pay something you can think of as a secure, or as an insurance ahead of time that allows you, in the event that you draw 2 reds in a row, and therefore you supposedly lose everything, having paid this insurance, you have a right to a third draw so that you can minimize your losses. And for example, this is one example of what, in a jar that has the probability of red goes between 0.2 to 0.8, these are the expected value of the risky, the riskless, and the reduced risk. And you see that for various regions of this range, each one of these 3 options is the one that is best in terms of expected value. And the thinking is that the risky is essentially like business as usual. Riskless is impose very, very strict and immediate and harsh reduction that will eliminate the risk altogether, and reduced risk is somewhere in between. So, okay, there are some decision aids, which is the way in which subjects are presented with this information. They don't show up, so I'm just going to skip up here. To give you a sense, a flavor of the results. This is how the pattern, the attractiveness or the probability of choice, they're not exactly the same, but they're highly correlated, change as a function of vagueness. Vagueness is the range of probability. And you see that as there's more and more rangeless, people get away from the risky, and people increase their choice of the riskless. Okay? So, and this is how, again, you didn't see the decision aids, but there are decision aids that present this information in a different way. And the interesting thing is that the attitudes, the control is where they have no decision aids whatsoever, and these are 2 decision aids. And you see that the proportion of choices between the various options also vary as a function of the way things are presented. So that's something which is very, very profound, very simple in some sense, but profound, because it drives home the idea that the way you communicate probability, the way you explain them and show them, can affect in very, very dramatic way the way they are going to be used in decisions. I'm going to skip this, just a pattern that shows how when people choose risky and when riskless as a function of the probabilities. Here's an interesting thing. As I said, this is the gray area between decision under ignorance and decision under risk. So what we did, we used this data and fit a bunch of models, some of them taking from decision under risk, some of them decision under ignorance, and we calculated the degree to which they fit the data. And the 2 best models are the maximin, the very conservative maximin, which of course in this case doesn't involve probabilities, and one where people say, let me assume that the probability of red in the urn is exactly the probability that in the observed part, so 40 to 30, and calculate expected utility accordingly. And for relatively low levels of imprecision, they fit equally well. But the more imprecise the range becomes, the maximin becomes the dominant. So people can adjust their strategy, and they tend to choose different decision strategy as a function of the imprecision in the urn. Okay. There's, again, a generalization in the literature. People dislike imprecision. Well, not always. Here's an example of a study that it's now being reviewed, where we find a place where people actually like imprecision, and we can explain why. So in a financial context, companies that are publicly traded, they have the option, totally voluntary, on a quarterly, on annual basis, to equal predictions to their shareholders and to analysts of what's going to be, what are the expected earnings per share. We analyzed here almost 35,000 quarterly forecasts from almost 5,000 companies over this range. And some of these predictions, some of these forecasts that management issues are in the terms of 3 cents per share. Some of them are higher than, some of them are between. And this is the proportion of the shares, that's what the management issue, which are in fact ranges. So first of all, you see that companies, when they issue this information, this forecast, they stay away, at least in particular in recent years, from precise. So one questions why it is that they are communicating imprecisely this information. And one of our hypotheses is that because they think that that's what the public, in this case the target audience, in fact prefer. And so we did experiments where we showed people kind of short excerpts from release to the public release. What are the projections of that company? And we asked them to rate them on a variety of scales. And we asked them which one would you purchase, if you had the option. And essentially what we find is that as a rule, most people preferred to purchase things in which the forecasts are issued in terms of imprecise as ranges over the precise one. And this is more pronounced when the information is, when there's a case, there's a cue that there is underlying uncertainty, and when the vagueness is low. And when you ask people to rate them, what you find is they think that this reporting or predicting a range rather than a precise number, they find it to be more informative, more accurate, and more credible. So our interpretation of these results is that this is one of these cases where the management has this good sense that in order to match the expectation of the public, you need to report things at a level of precision or imprecision that matches their expectations about the environment in which these are issued. Okay. So I'm going to move to the second part of my talk, which is about probability words. So here are some results from the literature on probability words. First of all, if given the choice, would you rather communicate probability by saying it's 0.37 or by saying it's possible or probable, there's a very distinct, clear pattern in hundreds and hundreds of papers. People prefer to communicate to others verbally. People would rather say it's likely that or it's possible that. And they prefer to receive numerical communication. That's kind of a very asymmetric pattern. But there's a strong preference for communicating to others verbally. People, when left to their own devices and asked to choose their words, people have very, very large and very idiosyncratic and very widely different lexicons of uncertainties. Sometimes we run experiments with 20, 25 subjects, and when you look at the data set, there are almost 200 different expressions of probability, verbal expression of probability that people are generating. And most interestingly, people disagree with each other in the way they interpret these terms. In other words, when we ask them to translate them back into words. So here's an example. This is a slide from a paper of ours in 1986, which was then redone, and I think it shows up in all the IPCC reports or guides, where essentially you see that for each one of these words, such as unlikely, improbable, this is the range, and these boxes are describe the range of the individual lowest and highest values. And you can see that many words span very large ranges, and there's actually there are large differences into what's the highest and lowest value of the word. Okay, so this creates what we've called an illusion of validity of communication, because you think that everyone understands the word, I said likely. How can they misunderstand me? But in fact, if different people use different words and I use them different way, my likely is not your probable, okay? And so the challenge here is to try to come up with ways to either translate these words efficiently from one to another, and this is complementary, finding way of communicating the information in a more efficient way. So I'm going to very quickly tell you about my favorite way of doing translation, which is elegant but takes a lot of work, which is to start with a model and saying that to model the meaning of any particular word, you fit what we call, I mean, we borrow the term from fuzzy set theory, a membership function for each word. So this is the membership function of the word improbable. It is bound, it's got between 0 and 1. The 1 is for a probability that fits exactly precisely the term. 0 is something which is outside of the meaning. And of course, everything else has intermediate value. So this could be improbable, this is likely, and this is certain. As a rule, these look maybe like probability distributions, but they are not, because they could take, they are not, you know, they are not densities. The area doesn't have to be 1, and they can take all kinds of shapes. As a rule, they are single-peaked with a few which are, in fact, monotonically increasing or monotonically decreasing. And the idea in our translator is the following, is that you present to, and you can do this in a particular community, say with intelligence officers that work, military intelligence, CIA people, who work using these words all the time. You can trace or encode the shape of these membership functions for various words, and then find ways of translating them from one to another. So here's an example. One way to translate them would be to say that if two judges, one and I and J, these are their 3 words, what you are doing, you are ranking them according to the locations of their peak, and then, you know, and then the translation is that one's unlikely matches on impossible, the somewhat likely matches that is a chance, and so on. So that's the way to translate. An alternative way to translate, which is more elegant but doesn't actually work that well, is to basically choose. I mean, this is a chance, and this is your unlikely, somewhat likely, likely. I can impose mine on top of each one of these and find the one where the mean absolute difference between the membership function is minimal. Say that's my translation, and so that's another criterion. And so, and there are others, but in the interest of time, I'm going to skip them and just to give you a sense of some results. We're in an experiment. We're in 2 experiments here, in which we ask people to, we traced their membership functions. It's relatively easy to do. And then we asked them to make up many, many judgments about events. And then we looked at the level of agreement. And these are 2 measures of agreement. And one is more conservative than the other, doesn't matter. Let's look at this one. And you see, when you use numbers as a control, people agree 68% of the time on the number they assign. These are numbers rounded to the nearest point of 5. When you use words, they only agree about 26%. Now, can we improve upon this through translation? And the answer is yes. And you see that when you use this translation, the numbers jumps for words from 26 to 67, 78. In fact, in some cases, they're even better than numbers rounded at this precision. Another way to show this is simply just to express this in terms of, if this is the baseline, so express simply how much better you're doing with each one of these translations. And then we ran a second experiment, which was even nicer, if I may say so myself, where we used the subject foreign graduate students from various countries. So there are people who are speakers, native speakers of French, Turkish, Russian, Spanish, and we had 2 other languages, I can't remember. And each one of them used his or her own vocabulary in their own language to communicate, to make the judgment of the probability. We asked them to bring with them to experiments dictionaries, and we looked at the actual translation, and we wanted to see how the comparison we get to the membership functions compare with the baseline, which is the dictionary. Okay, so that's the standard translation for the dictionary, and you see that with our method of membership functions, you can do much, much better than with the dictionary. So in some sense, it's possible to come up with such an event. There are other ways of doing it with something called probability signatures. I'm going to have to skip this. Do I have 2 more minutes to talk? OK, so I'm going to talk about the talk, again, something related to climate change. That's the paper that, if you're interested, is on the website. So what we did, the IPCC, that's the IPCC solution, of course, to dealing with uncertainty. They tell people, use this vocabulary. And by the way, if you look in the intelligence, medical, and many other literature, there are many, many, many papers that have vocabularies of this type. Okay? But that's their choice, and it's a perfectly reasonable choice. Although I must say it's ambiguous because it says likely greater than 66, very likely greater than 90. It doesn't say that likely is 60 to 90, 66 to 90. So it's conceivable for someone to interpret likely and unlikely in different ways. So that's ambiguity. So anyway, so that's the scale that they are asking the writers to use and to keep in mind whenever they communicate uncertainty. And when we read the more recent report, we asked ourselves, okay, that makes sense, but is that the way the readers will understand it? Okay? So what we did, we ran an experiment in which we pulled out 13 or 14 phrases from the report. So this is one of them. It's very unlikely that hot extreme heat waves and so on. We underline, we highlight the term, and you ask people to move these sliders such that they will stop to find the location that represents the best interpretation of what it's meant, what's the lowest, and what's possible value. So we ask people essentially to look, to read them, and to find the range and the best value. So, I'm sorry? That's the control. The second group had also access to this translation when they started, and there was a button here where they could click and see it again every time they wanted to. Okay? So these are part of the results. And here, let me show you to explain this plot. So these are 4 words: very likely, unlikely, likely, very likely. Each one of these box plots is a Winsorized, 5% Winsorized. So the difference between the lower and upper bound are the central 90% of the distribution. This is the central 50% of the distribution. That's the median. And these numbers, and the direction in which they are plotted, indicate what proportion of the people assigned a best value which is outside the range prescribed by the IPCC. And the first thing you see from this direction is that the interpretations are regressive. They regress to the mean. So high words, there are more misinterpretation closer to lower, low probabilities, most interpretation in that direction. And having access to the table improves a little bit, right? 79 reduces to 67, 75 to 58, but it doesn't strike you that we got it, okay? So we thought maybe we can improve a little bit by actually taking the trouble of actually including the numbers in parentheses next to each word. And sure enough, it helps. It helps, and again, the same kind of Winsorized box plots. And you see that now there's a much, much better, the rates of misinterpretation are now reduced, 73 to 53, 49 to 37. So, so I think it's in itself a small step. But what I think is even more interesting here is the following: is the fact that if you have the option of including next to each term a range of values, you are no longer bounded by one table at the beginning, and you can use for different words different ranges, and so they have ways of communicating more effectively and precisely the uncertainty. And we did another variation in which in one group we included the original ranges that are in the APCC guidelines, and in another group, just to see whether people will react to that, we reduced the ranges by 10%, I think, or 15%. And again, you see that this is effective. People are sensitive, 54 to 51, 40 to 35. People are sensitive to the ranges that are being communicated to them. So to summarize this, because I think I'm going over my time anyway, it is possible to translation to reduce, but not to eliminate miscommunication. And it's possible to find ways to communicate improbabilities more precisely to a public, to a naive and unsophisticated public. So to summarize, these are my last two slides. I think behavioral research in JDM is important in this case because it provides you a window into how people who are user or audience of the uncertainty that stems from the models and the parameter, but eventually filters down and gets to the public and shows up in the New York Times and LA Times and in all kinds of congressional briefings. And it's important to understand how this communication, how these values are being used, and some of the common wisdom that people believe about ambiguities are not quite as common and not quite, and I think that people are overgeneralizing. And I think that I have a few cues, a few hints about how to improve communication. First of all, the principle is that you need to communicate imprecision as precisely as warranted by the data, but not beyond that. And that's a good principle. It's not always hard, and not always easy to implement. I think, as our congruence hypothesis states, you need to communicate things in a way that matches the nature of the event and the underlying uncertainty. I think that any probabilities must be almost religiously be used only for events which are unambiguous themselves. And I think that you have to do a lot of work and a lot of pilot work and a lot of test, trial and error to find in each case what is the best way to communicate this information. The last thing is that I know there are caveats to what I'm saying. I think that you can take or leave any of the messages because my samples are primarily students, although they are students from many universities, but they are primarily students. We pay subjects for participation. All the choices were properly incentivized but for small amounts. And if you add several zeros at the end, it may change the way people are. There's a special problem with extreme probabilities. Things that are 10 to the minus 3 to the minus 4 to the minus 5. I'm not sure that anything I've said here applies to these ranges because they are very, very special and complicated. And also, I must admit, all this was done by bringing volunteers to participate in an experiment where they are we strip away any content and any context. They're not part of organization. They're not part of a political decision making. And of course, all these things will affect, there'll be a different layer. But I think what you learn from this is the basic cognitive psychological processes that underlie the way people think and operate with imprecise probabilities. So, thank you. Thank you.
Thank you very much, David. Can I invite all the speakers to the front for questions, please? Thank you. Can you use the mic?
I had a question about the food security. So on the food security, as I understand it, you estimated the amount of crop reduction due to climate change or the probability distribution on it. But in some areas, there will probably be increases in crop yields. So what about the total? Did you make...
So for a specific crop, these were aggregated as a global average. So we come up with deltas, either positive or negative, but it's aggregated as a global average.
Yeah, I wanted to comment about ambiguity because I agree with you that that's the right, that ambiguity should mean statements with an indefinite meaning. And I think coming out of a theory of unawareness, that's precisely what you get. You get ambiguity fundamentally meaning relative to the perfect description of the state space. Your descriptions about the state are ambiguous relative to the hypothesised unbounded rational person, and also, though, typically in interaction. Ambiguous in the sense, I have a paper with Simon Grant and Jeff Klein which precisely does this, says we have contracts but the people have different interpretations of what you get from them. And then I'd assert that imprecise probabilities are derived, they are to do with ambiguity because whenever you have ambiguity of that kind, you also have imprecise probabilities. And so the correct way to give Ellsberg credit, when he picked this word more or less out of the air, I think that the intuition does seem to be right, that if you aren't precisely describing the world, then you can't have precise probabilities, which is exactly, I guess, what your respondents are finding, that they only like precise probabilities if they think the description of the small world in question is in fact precise.
But when we feed to data from our experiments some descriptive models, we find that when people make choices, the degree to which the imprecision or vagueness or ambiguity it's a very important secondary or sometimes tertiary criterion. In other words, when things are very close in expected value and the distribution is very, very similar, then that becomes a way to break the ties. But it's hardly ever, the first criterion that explains choices. Yeah.
you give a very good caveat that we so far lack a super sample. So you either sample structural uncertainty or you sample parametric uncertainty. Now, given the fact that some of your statements about risk depend on tail area issues, how is a decision maker to interpret your results about the PDF, especially about extreme tail area events, given that, for example, the structural uncertainty Bayesian model averaging of the structural sample doesn't really go into the details of the parameter PDFs. So what do you think, how should we communicate this? Is this going to be a big effect or small effect? Should we just wait for until the analysis are done? How do you communicate?
Okay, you're going to uncover the schizophrenic side of myself, which is I like to work on this kind of studies, as I said, because I think there is the need of formalizing statistically how to look at this data and try to account for most of the peculiar characteristics of this data. But I'm very skeptic right now that we can come up with precisely characterized PDFs, especially when you talk about the. Oh, thank you. I felt like you were interrogating me, especially when you talk about tail probabilities. So I'm the first one to say that when it comes to actual decision making, we are far from having characterized that extreme behavior and. But I do think, there is the need of exploring this more systematically, more rigorously, and that's why I was trying to say that in an ideal world we would do both PP, perturbed physics, and then look at multimodal ensemble of perturbed physics, and until then I really don't know what to propose. So I really I'm kind of stuck myself when I think about this, and I was the reason I was not here yesterday is I was in Washington because there is this panel now on stabilization targets, and the entire idea is to try and characterize the different futures that we could, be in by stabilizing concentration at certain levels, and it's all predicated on trying to find differences in the outcome at 350 rather than 450 rather than 550, while we know that there are these humongous uncertainties so anything that we see under one scenario is going to spread out, and so I really it's going to be a hard job also on that side, but I totally agree with you that it's a big problem. Nevertheless, I think we should work on it.
I had a question about communicating risk. I was wondering whether there's been work on using other methods of communication, either graphical or by trying to give people anchors to common situations, where they might be familiar with, like instead of saying 0.5, saying flipping a coin. Do those, if there has been work like that, do either of those approaches help?
They help to some degree. There are a couple of papers, for example, in probability, there are a couple of papers by, what's his name, from Carnegie Mellon? Granger Morgan, and his collaborators that are kind of showing PDFs in a variety of displays and asking, and they. I'm sorry?
That's the thing where they took uncertainty displays around to a
right.
bunch of decision makers in EPA.
Right. So there, I don't think that there is any study that says there's a particular method that is, universally and always better for all instances. I think that some principles from some literature reviews about communication of risk is that graphs are very efficient. Graphs are always even more efficient if they're accompanied by, good and short and concise description, on probabilities, and especially if you find the right graphic display, one that has that highlights what is salient for that particular context, which is sometimes not easy to. It's sometimes easier to determine in retrospect rather than before. So, yeah.
Okay, thanks.
Can I ask a question of the other?
Okay, after that I'll ask a question to you though.
So I'm interested in this idea of downscaling from the global to the regional models. And it seemed to me that in most of those cases you showed, there were, at least it looked to me, kind of arbitrary decisions to what scale to decrease. And I didn't see a function that shows what is the sensitivity of the value-added information as a function of the resolution of the regional models.
I'm not an expert, okay? But and maybe Bill can add. But I mean, there are a lot of studies that have addressed both the domain size, which is also very important, as well as the scale of resolution. But Bill, you want to jump in, please? Help me.
Well, I think the result that you showed that was very telling is that a lot of the value added is coming in regions of orography. So in essence, what that's telling you is that the internal model dynamics in physics aren't really buying you much. It's changing a boundary condition that's buying you the additional information. You're resolving range shadows better. And in some sense, I think that's an important result, but it's not, what it's telling you is that it's not the model itself, it's the fact that you're wrinkling the surface of the Earth a little bit better. And we actually don't, but the deeper answer to your question is we don't know whether these models actually converge to the truth as you take them to infinitely high resolution. And in fact, there's very good evidence that they don't.
Thank you. Might I ask one question and then Fulya? We had now, actually different probability distributions, and I think also Claudia tried to convey that she's not convinced that the one PDF that she produces is actually the one that describes the future necessarily correctly. And then we had the ambiguity models yesterday where we were actually thinking how to deal with having different probability distributions, multiple prior models, or the KMM model. And then we had David actually presenting also this evidence about the Ellsberg paradox that yes, like a third of the individuals probably showed ambiguity aversion, but some even showed ambiguity lovingness in that language of yesterday. And if we try to think about it normatively, like what should we do with the information that you convey? Should we kind of look at, like, take the probability distributions of your method? Should we combine it with probability information we derive from perturbation models? And then should we plug them into, for example, the model of that Sujoy presented yesterday that you haven't seen? But if we do that, should we take ambiguity aversion in there? Would you say that we should take account for that additional variability between the probability distributions in the sense of punishing it? Or if we also have this experimental evidence here that is not as, going to either direction, actually.
What is the question? Because it's so complicated. I have a hard time, I don't study these things, so I have a hard time thinking about this in an abstract sense. And I think it has to be grounded into specific decision and specific area of applications. And my hope right now, given all, given how untractable this seems to be, is that there can be decisions that can be taken even with very loose characterizations of this uncertainty just by using some kind of cautionary principle or some, mini-max or max-min approach. So I don't think I have an answer for that, and maybe David has a more informed.
I don't have an answer, but I have a message, and I think that all this meeting and many meetings like it are all very, very concerned with the deep uncertainties underlying the models and underlying the parameters. I think there's something to take away from my presentation is that there are equally high, there's equal high imprecision in way in which individual decision maker is going to interpret the results. So the way the same information is conveyed to different people if the same information is conveyed to different people doesn't mean it's going to be interpreted identically. And that I say, and I don't have a solution to how this is, but I think that this should definitely be part of the equation and of the planning. Yeah.
referring to the last presentation, we talk about communication, but also risk perception or ambiguity perception. That is quite different from evaluation of a consequence and the risk assessment of probability or consequence. With respect, we have also to consider that often risk that or events that we would like to communicate are extreme risk with very, very low probability, and the capacity of the interpreter, this probability is very, very low. For example, I would like to refer a close example with respect to climate change. And there is also another variable that is relevant in evaluation, time. Present is different from the future, and people have a different attitude with respect to time discounting. For example, in the case of infectious disease, in the case of swine flu and avian flu, you have a very similar attitude. More than in the case of the climate change, you have a very, very affordable or probability, more or less 3% of a pandemic flu in the next year. That was because we know that there were at the last 3 pandemics in a century. And the consequence of this event could be very, very catastrophic in terms of human life, for example, because the fatality rate in the case of avian flu was more or less 60%. And you have a clear, or not clear, but in some sense, configuration of a possible response to this terrible events. Antiviral, for example, at the best of our knowledge, there exists at least 2 antiviral able to block the diffusion, the spread of the disease, and the possibility of producing a vaccine. Many countries reject the production or the selling of antiviral because the probability was very low or because budget constraint. Now we are facing a certain event that is the swine flu. That is true, has a quite different characteristic at now, but we don't know if it becomes a sort of Spanish flu because it is going in the same path of this terrible. So I think that when we communicate this kind of risk, we have to concentrate on the consequences, and we have to give a clear representation of this consequence in terms of interval of time. This is my view.
Yes, I have a question for our last speaker. I would like you to comment a bit more on the experiment you've shown us on of the stock market, right? The one that, in your words, seemed to show a preference for vagueness or a preference for ambiguity. And the reason is that because, as far as I understood, you've shown that when comparing a choice between a precise estimate or a range of estimate in the stock market, and I should add, whose intermediate level correspond to an expected value that equals the precise one, otherwise you cannot compare the choice. But in that case, people seem to prefer choosing the stock that has the imprecise one, which is, by the way, an example applied to the stock market of the two-color Ellsberg urn. It's the reverse behavior of the two-color Ellsberg urn. Now, what this example shows, at least the way I understand it, is something that we have been talking about yesterday, that is the mixture of ambiguity and ambiguity attitude. Applied to stock market, because and what it really shows is that perhaps, according to my opinion, is that when making choices in the stock market, people tend to be optimistic, tend to be ambiguity lovers. By the way, this is not Why? Because then in that case they take the max of the range, and the max has an expected value higher than the expected value of the precise estimate. By the way, this is not a novel result. I mean, for instance, there is a paper by Cox and others in Journal of Risk and Uncertainty, I don't remember the year, showing that at least professional traders have a subadditive decision weight, that is to say, they show optimism. So what is really what one really would like to know if you want to say that decision maker in some case has a preference for ambiguity instead or for vagueness instead of preciseness, is to disentangle the ambiguity and the ambiguity attitude in the experiment, and showing that there is a preference for ambiguity apart from any specific ambiguity attitude, which is, of course, is difficult, because when you make an experiment, then most of the case, like in this one, you mix up the ambiguity and the ambiguity attitude of the decision maker.
I mean, I'm not sure I can answer precisely, because, I mean, that's not the way I was thinking about this experiment. We were thinking of, we were struck by the high proportion of firms that choose voluntarily, A, to issue this forecast, and B, by the fact that contrary to what is the normal expectation, they don't wish to communicate to analysts and to potential investor precision. Now, if you ask them, they will probably tell you that one of the reasons they do it is because they're afraid of litigation. There are all kinds of other reasons that can explain, and I think what was interesting to us is not so, is the fact that the intuition of the firms using this kind of forecast matches the intuition of the MBA students who were subjects in this experiment. And so the sense that they perceive this to be more credible and more informative. In other words, that people don't always expect information to be precise, and precision is not always a virtue in and of itself, unless it is in situation where you think there are good reasons to be precise. And see, if people know enough about the stock market to understand that it's extremely important, it's extremely difficult for a particular firm to say 4 cents per share rather than 5, they appreciate and they value, there's a signaling there, which I think it's important to investors. And by the way, since we had the actual predictions, forecast, we could test how calibrated they are, and they are dismal. In other words, the hit rate, I mean, the proportion of actual quarterly shares, I mean, earning per share that match, the predictions are between 20 to 30%, and of course, with ranges they are larger. But they are larger, not proportional to the length. So it's not simply larger by chance because you have more opportunity, but in fact there's no relationship, there's no correlation between the width of the interval and the hit rate. And we calculated how much on average you would have to increase those ranges to meet the standard confidence interval, 90% confidence interval. It's by a factor of more than 10. For quarterly, it's by 10 or 11, and for annual, it's even more than that.
So Rob and Sujoy still had a question, and then we probably go to the break. No? Okay, just Rob. Okay, cool. Perfect.
Yeah, actually, I wanted to sort of offer an answer or some thoughts on your question to Claudia and David and tie some things together. The water results I showed yesterday were using an earlier version of Claudia's PDFs, and we actually used them in 3 different ways, both to kind of create individual scenarios of adverse and benign climate. We used her PDFs just straight up, and then we used them as essentially an upper and a lower bound anchor for, best worst case in a context where we said, well, actually the models don't reproduce the variability we even see in the past very well. So these are sort of a structurally uncertain lower bound, and it could probably be worse on either end or either end. And then we tried as best we could in the context of workshops with real decision makers and elected officials and all that sort of thing, to reproduce the sort of experimental design that David showed you with the EARN experiment, trying to see what people understood and responded to the different ways we took the information from the PDFs. And so very roughly, there was sort of trade-off between complexity and usefulness. And so, you know, the simpler it was, the more they understood it and felt that they could explain it to other people, and the more complex it was, the more useful they thought it was, but the more difficult they would think it was to explain to other people. And this was all then also mediated by they were more willing to believe potentially adverse cases the more they thought they could do something about them. So you kind of had to convince them that they could do something about them in a way that wasn't too onerous. And once you'd done that, then they would be much more willing to believe that they might have a serious problem. So anyway, that's